So he's an assistant professor in the Faculty of Education at Simon Fraser University. Now, Sean's interest lies in the integration of digital technology into mathematics teaching. And he's also currently looking at teachers' development and the use of digital tasks to reorganize mathematical practice. So he's going to talk about something called gerrymandering, a demonstration of how mathematicians can raise awareness and imagination. So join us for the next 60 minutes or so to find out how math is more than just numbers.
I would also like to, just because I feel a little more comfortable acknowledging and thanking the Coast Salish people for whose traditional territory I'm currently located. I'm actually currently in North Vancouver, and so I particularly express my gratitude to the Squamish Nation and the Tsleil-Waututh Nation. I know all of us who are tuned in are distributed across a great area covering many traditional territories, and so I hope we can be grateful in our own way and for being where we are. Thank you so much for tuning in. This is a unique situation, as we all know. I think most of us have taught online and know the challenges. My presentations are typically interactive, and so this is a bit of a challenge. I don't know why this has turned into a bit of a lecture, but I think I'm going to be talking probably for 40 minutes, although I will break it up a little bit in asking you to do a few things. And then, of course, we'll have discussion and questions after. If you do, in fact, have any questions while the presentation is ongoing, please speak. There's a very good chance I won't see you. So you can unmute yourself and say something. This talk is based on an Insight Development Grant that I was awarded this year, as well as some work that I've been doing with some Vancouver teachers in the Vancouver School District. I myself was a math teacher for about 20 years, over 20 years, in fact. In Vancouver before I came to SFU. And you'll see my tendencies. As a teacher, I'm very interested in classroom work. I know there's wonderful projects going on outside of classrooms, but my work is I'm interested in classrooms partly because that's where I spent much of my career, and I think that's where still a lot of students spend their time. And so trying to make mathematics as authentic and as meaningful as possible. If I were to summarize my research in 3 words, I would say it's mathematizing social issues. And most of today's talk will be about explaining what that means and how it works. There's a lot of work to develop in terms of my activities and planning, but what I present today will be a gist of where I'd like to go in the thinking and planning so far. While the focus of this talk is mathematics education, I hope that you do take away some ideas, not just of what mathematics can offer, but also just how we can think different ways about integrating different disciplines. I'd like to start off though with a card trick that I like to do. And this is the second half of a card trick. The first half is it's an unfortunate term, but it's forcing a card. So I get an audience member to choose a particular card. So I know what their card is. And then I lay down a 4x4 grid on the table. And I didn't know how to present this by video. So Quincy Wang actually made a little video. So I'm going to play that video now. But what you'll see is you'll see the grid of 4x4 cards, and the purple card is the card that I want them to choose. So here are there 16 squares, and I want the person to pick the purple one. I ask them to draw a line through the squares, between the squares, anywhere they want. So if they draw a line here, then I eliminate these. And then I say, you have free will, free choice. You can draw a line wherever you want. So they draw a line here, and I get rid of these. And then I say, draw another one, and they draw here, and I get rid of these. And then I say, draw another one, and they draw here, and I get rid of these. And then there's 2 left, and I say, choose one for me. And they choose this one. I say, thanks, that's for me. There's your card. So the reason it's called a card trick is because it's a trick. And as you can see, I'm controlling what cards remain and what cards are discarded. So while the audience member might think that they are freely choosing what cards are being discarded, their choices are meaningless. I'm in control of what's going on. And I know some of you are familiar with this trick, but I am going to bring this up later. There's a point to this, and I'm going to refer to it. So what is mathematizing? I'd like to just start with a quick story. There's a story about Agnes Martin, the 20th century abstract painter, who a girl goes to her house and picks a rose in the front yard and is holding this rose, and Agnes Martin says to the little girl, is the rose beautiful? And the little girl says, yes, it is. And Agnes took the rose from the girl's hand, held it behind her back, and asked the girl if the rose was still beautiful. And the girl said, yes. And Agnes reportedly said, beauty is in your mind, not in the rose. And although the story is about beauty, I suggest that the same applies to mathematics. The mathematics is about imposing an idea or a way of seeing onto something, rather than reading or eliciting information from it. And this is very important for me, because it advocates that mathematics is about choice and creativity, and that it's emerging, at least initially, from a student, or any person for that matter. And it's about us interacting with materials and others to develop new ways of thinking. David Wheeler, who was an adjunct professor at SFU in the late 90s, after a very distinguished and fruitful career in mathematics education, he describes the process of mathematization as the mental processes which produce mathematics in situations where something not obviously mathematical is being converted into something which obviously is. And the direction is from the mathematizer outward. And that's what I mean by directional. If you can see me right now, I'm pointing my finger away from my face, and that's the direction of mathematics. I'm not advocating for mathematics as being mental, but more so that it's directional and intentional to begin with. And in addition, since students who I want to mathematize are all different, we're going to have multiple sort of suggestions and possibilities and multiplicity in what they suggest. Freudenthal's notion of mathematics was that it initiates from those who engage in mathematizing, so very similar. And, but an interesting point that he adds is the idea of starting point of mathematizing is not theorems or discoveries of others, but simply the opportunity to make something mathematical. Mathematizing asks the student to organize information, to create a particular pattern, to reason with a reduced set of results. And although Burckhardt doesn't use the term mathematizing, he does, in his work with real life math problems, he does describe the need for students to have an active attitude, including questioning, choosing between different approaches, and trying to answer those questions they pose. And this is an important point because it draws attention to mathematics as being as much about the active person process than about the actual mathematics. The mathematics that the student creates is maybe not the same as the textbook or even in the curriculum, but it is a power they possess. So I have two stories to share with you about mathematizing. One of them is Thales from approximately 600 BCE. And Thales was in Egypt. He was contemplating the Great Pyramid of Giza, and he asked the locals what the height of the pyramid was. And no one seemed to know, probably for good reason. But Thales wanted to know the height of the pyramid. And it so happened, the legend has it, that as it was the middle of the day, or this sort of part of the day where the sun was at an angle, so that his height of the shadow was the same as his height, as you can see in the diagram. And so he was able to then recognize, well, then all I need to do to determine the height of the pyramid is to measure out the shadow. And there's a few other calculations, but the point being is to recognize his experience of the shadow with that of the pyramid. And notice that Thales was not studying mathematics based on theorems. He was contemplating, he was questioning, and he was reasoning with the notion of scale. And if our story stopped there, we might find ourselves in the same meta-narrative we often find ourselves with mathematics. Smart person, cool trick, not for me. But when we think about what happened here, we're talking about 600 BCE. There was no developed mathematics yet. Thales is not drawing on previous knowledge. He's creating a new idea. he's accessing the inaccessible. Because back then, of course, they didn't have tools to measure the height of a pyramid, or at least not easily. And delving even a little deeper into what happened here, based on his experience, I call it substitution because he's replacing his experience and his observation of his shadow with that of the pyramid. He combines the likeness of the situation, the shadow in this case, and substitute his experience to reach the inaccessible. And in some ways, this is a bad example because Thales was a legend in mathematics. He ended up being a great mathematician. So again, we find ourselves in this position where only mathematicians can do mathematics. But no. In 1435, Renaissance architect Alberti from Italy described a process of how to depict three-dimensional external reality. And he asked the architect or the painter to imagine a transparent screen between them and what they were trying to depict, to draw. And on this transparent screen, he asked the painter or architect to imagine lines of sight coming from the outside world through the transparent screen to the eye of the observer. And then to mark, imagine again, to mark on this transparent screen the pertinent points, the important points of where these lines of sight pass through. And then even more interesting is that he inverted that cone because ultimately we had external reality coming to the eye of the observer. We now take those points on the transparent screen and invert the cone. So now that the cone is going into the picture, and so the apex of the cone is at what we might call a vanishing point or a horizon line. And therein lies this process, what we call now linear perspective, of an architect creating a method to depict three-dimensional reality in a two-dimensional space, realistically. And again, I don't want to perpetuate myths that Alberti didn't work from previous scholars and writers. It took several generations as well for these new techniques to become established. But the point is not so much who was doing this, but that it is an example of mathematizing. So both in Thales and Alberti's examples, we see a mathematizing of something not apparently mathematical. We involve not knowledge, but imagining a new way of seeing, a way of crafting materials and ideas, a creative method that didn't seek truth, but valued inquiry. And it's about crafting an approach to something that's not definitive, but possible. So here we have a right angle triangle. And one of the features of mathematizing is that it embraces multiple relationships. In this particular, like Thales and the shadow with the pyramid shadow and Alberti with the transparent screen and its relation to three-dimension in relation to two-dimension, we have these relationships and they're not always visible. And it's in this particular triangle, right angle triangle, there's multiple relationships. One of which you know is Pythagorean theorem, that the sum of the area of the squares on the two shorter sides add to the area of the square on the longest side. And Whitehead is a mathematician, a prominent mathematician and philosopher, and he writes that a defined, can't quite read it behind my, that it's a defined pattern, such as a right angle triangle, does not always disclose its intricacies to immediate consciousness. And he says it in this very philosophical, obscure way. But the simple idea here is that the relationships are not always obvious, that it takes investigation, that by engaging in mathematizing, new relationships emerge. To carry on with that idea, I'm missing a slide. So as I said, I'm missing the slide and there's a chess image of a chessboard. But Dave Hewitt talks about the arbitrary and the necessary. And he talks about mathematics as being a unique discipline because there are certain features that are arbitrary, such as names and rules. So for instance, if you imagine a chess, the game of chess, if you were to give someone the pieces of chess they wouldn't be able to figure out the game of chess because the rules of the game as well as the names of the pieces are arbitrary. But once you give a person the rules, they can, through analysis, come up with necessary conclusions, such as two knights, the two horses in the game, can't checkmate a king. And so there are sort of necessary conclusions to arbitrary rules. And this is similar to Whitehead's idea that there are hidden relationships. It's this idea that mathematics is about investigating relationships and how results come about after mathematizing. Let me share with you another example of mathematizing that comes from my own teaching. And I wonder if you can look at this problem and just think about it for a moment. And this, by the way, is a classic math problem. It was used when I taught in the early 90s, and it's still being used today. And it's used to practice a maximizing and minimizing algorithm. The current price at a theater is $6, and the theater can hold 300 attendees. For every increase of 50 cents, there are 8 less attendees. What should be the price of a ticket to maximize revenue? I'm not asking you to solve it. I'm asking you just to look at that, just to think about that for a moment and what it's conveying. One common way to teach mathematics is quite often to teach a procedure and then to practice it using some kind of application. It's the way to justify the mathematics and to motivate the students to see that mathematics is used in the real world. Unfortunately, these applications are quite often economic or engineering-like, and that's why we see the popularity of STEM, where mathematics has to be associated with science, technology, or engineering. Thank goodness for A. STEM has been converted for some to STEAM, where A stands for arts. But I'll tell you what I notice, and here are some of my observations. And the first is that it's an underlying assumption that the student is meant to implement a particular procedure. The students are usually aware of this assumption. Also, the problem is prepackaged, fully articulated, just right to convey exactly what needs to be practiced. So those are two problems with applications that I believe mathematizing social issues gets away from. But what's even more pertinent to this particular point is that number 3, and that is that the problem implicitly conveys that revenue is valued more than the collective aesthetic experience of a full theater. And in fact, the solution is that there are 102 empty seats and that the ticket price should change from $6 to $12.38. So, you know, that's quite astounding, I think. So when I taught that problem back in the early 90s in grade 11 class, I went through the whole process. A student at the back of the room raised their hand and asked, what if our goal was to fill the theater? This is a true story. And it was the initiation of my own interest in social issues and the connection to critical mathematics, which scrutinizes, you know, what is it that we're teaching in mathematics? And the question of the student epitomizes my focus in this presentation because it brings up how mathematics can be used to think about various social situations. I'm not against the original question. I'm only suggesting mathematizing provides mathematical insight into the different situations. So this student's question is not just a new perspective, it's a mathematical question that varies the situation for further exploration. The student didn't say, well, this is wrong, this is not right, but just simply posed a mathematical question. And in fact, Brown and Walter in their book, The Art of Problem Posing, advocate for the what-if questions. They describe the what-if method as a way for students to get a sense of the mathematics using alternate formulations of the original problem. And the point is just simply to get students to explore. So if we were to reconsider the triangle I showed you earlier, we can ask ourselves, what if the geometric shapes are right-angled triangles? are equilateral triangles. What if the geometric shapes on the sides of the right angle triangle were semicircles? Does the original relationship still hold, that area A plus area B equals area C? And surprisingly, it does hold. So let me finally give you an example of what I mean by mathematizing a social issue. This is an example I've worked on with students, with teachers. I've had a lot of success, and I've sort of developed this, this lesson. But as I said, you know, this whole project is still relatively new, so there's a lot to be worked out. But this is partially relevant as we have an election coming up, as does the US. And so here is a table. And I want you to imagine it as a great geographical area where P's represent a population that supports political party P. And the C's are a population that represent a political party C. There's just two parties. And I would actually like you to do the following. Using all the cells of the table, create blocked areas of 5 cells by outlining them. So for example, that would be an example of blocking off 5 cells. You could do horizontal, you can do upper left where there's like a Tetris piece. And I want you to tally each of these blocked areas using first past the post principles to see who wins. And first past the post is just simply majority wins. So in the top left corner, we have 3 C's and 2 P's. So C's win, the political party C wins. And same with the horizontal bar at the bottom, it's 3 C's and 2 P's. And I know that I'm really not going to give you enough time to do this because, well, it's partially, it's a little bit challenging, but I'm still going to give everyone 2 minutes. And if you are good at Zoom, you could even write, I think, on my screen. But yeah, just spend a couple minutes looking at it at least and thinking about what are some of the possible outcomes of different district boundaries, of redrawing. You don't have to use the ones I've started here. And you give 1 minute, not enough time at all. Beautiful. It's like a game. Okay, as I said, I didn't give you enough time. Part of the reason I wanted you to do this was to just sort of think strategically and to think about how you could, in fact, well, that there are many solutions or many possibilities. So I'm going to go to the next screen. Thank you for participating, blue, pink, brown, and squiggly. We want to get rid of those. Let me just erase that. So these are the 2 extremes of the various possibilities. And if you notice on the left, party P wins 1 seat and party C wins 8. So C wins 8-1. And on the right, party P wins 7 seats and party C wins 2. That's a significant sway. Realize the tables are the exact same. The letters are in the exact same place. The only difference is how the boundaries have been drawn. And I'm not sure if you can see the strategy, but the strategy is what is called packing. And that's actually a term they use in districting. The P's are packed on the left and the C's are packed on the right. So you basically give your opponent, if the C's are in charge of drawing the boundaries on the left table, the C's are packing the P's in one district. So they win 100% of the vote, but they're using a lot of P's in that particular district. Similarly on the right. But once again, that's a significant sway. And so I'd like to offer an interpretation of what just happened. First of all, the table I gave you initially was not mathematical in any way, really. It was just a bunch of letters. Maybe they were slightly organized, but it was just, there was not really any meaning until I gave you a little bit of instruction. And as soon as you started outlining and creating areas of 5 cells, mathematizing becomes evident. Why? Well, because it was directional. You were doing it. It's creative. There's multiple ways of doing it. And each outcome conveys something different. We have significant sway in how these outcomes are presented in this case. And presenting the table and asking students to draw boundaries, districting, if you will, the students have to follow arbitrary assumptions and rules. One has to follow the boundaries, as you can see. They have to enclose each district. And many of these ideas align with districting in general, in that districts have to be contiguous, they have to be connected, similar populations. The population of each of these cells has to be similar, just like it is in real life. They have to be within 5% of each other. Mind you, on the other hand, though, it's quite simplified too. There's no geographical barriers, populations are equal in each cell, and so on. I think I just wanted to convey that it's important to note that that particular table of C's and P's is not special. You might think that that's sort of designed so that you can get such sway. But one of the things I've used with students and teachers that I've worked with is I've given them an empty grid of 16, 4x4 grid, and I've asked them to arbitrarily place 8 X's and 8 O's, and then to outline districts of 4 cells so that we have X's win, and then to do it again with O's winning, and then to do it again with, to make it a tie. And in fact, almost always, those are all possible. And so the point being is that that particular table I showed you a moment ago is not special. Any table would do the same kind of thing. But of course, there's multiple ways of changing the setup of these tables. You can have more X's than O's. You can do not just four cells for one district, but 5, et cetera, et cetera. But once again, one of my purposes of my research is to explore how students develop mathematical awareness through mathematizing social issues. Is this a social issue? Not yet. Political. Now it's a social issue. Gerrymandering is the partisan manipulation of electoral district boundaries. Or I've heard other person describe it as carefully drawing district lines to achieve a political goal. And this is exactly what I had you do, although I didn't give you enough time, but I have students do as well, is carefully drawing district lines to achieve not a political goal, but a mathematical goal. And we explore the ideas of these district lines mathematically. Gerrymandering is illegal. It's something that's that one wants to avoid. It means the actual manipulation to support partisan control. And it's like the card trick I showed earlier. We think we are choosing our politicians, but in gerrymandering, the politicians are choosing us. And it's a real problem. But every time I read gerrymandering in any kind of literature or in book, it's always presented from a political perspective. But notice here, we didn't approach it politically, we approached it mathematically. We mathematized the table. We asked a question that I asked a question that got you personally involved, that you performed, but also then interpreted to understand the mathematical notion of gerrymandering, or at least of district drawing, rather than presenting it as a political issue or something that's just wrong. There was a prompting from me, but that's all I did. And yet it encouraged creativity, critical thinking, and multiplicity. Again, I may not make that claim here because I didn't give you enough time, but in the experiences I've had, and this is the research I'm continuing, is looking at students and the people that I've worked with in this activity, is that this is what I've noticed. Ultimately, my interest is how to improve mathematics. It's not so much to teach gerrymandering, it's to explore gerrymandering through mathematics. And much of the mathematizing is asking what-if questions. So, yeah, now I get dramatic. Now I throw something at you that's like a knee-jerk reaction. And I apologize that it's an American example, but it's a good one. Partly because it's just so staggering that the Democrats won greater than 50% of the votes, but yet only won 5 of 18 seats. This is the state of Pennsylvania in 2012. And if you look at the outlines of the shapes, they're quite odd looking, all of them. And I did some investigation of my own district that I vote in here in North Vancouver. It's also oddly shaped. And so it's actually not surprising that shapes are oddly, that districts are oddly shaped. But yet, why? And that's a question I pose to students. What is it that makes these shapes the way they are? One of the interesting shapes in this particular picture is the bottom right-hand corner, you see a red district, and it's actually been nicknamed Goofy Kicking Donald Duck, because that's sort of what it looks like, I guess. But what would ever make a district look like that? A river? No, I don't think so. So this particular case of the districting of Pennsylvania in 2012 was actually taken to court by the Democrats. And, but what's interesting too is, again, this idea of how do you prove that this was actually gerrymandered rather than just simply appropriate, the fair districting? And surprise, surprise, they actually had to bring a mathematician into the courtroom to prove, or not prove, but to describe and to try to convince that it is mathematically unlikely. But therein lies, again, this idea that gerrymandering is ultimately a mathematical topic. You have to redistrict. Districts are redistricted are redrawn all the time. Population change, immigration, whatever it might be. So there's always changes. So when does it become gerrymandered is a really interesting question. And another question I pose to students too is the idea of, what metrics would we use to determine the difference between something fair and something gerrymandered? And you can analyze this map geometrically. You can also analyze it numerically. I mean, 5 out of 18 seats, yeah, it seems significantly weird if your votes are greater than 50%. As I said, I do apologize for the American example, but it's... the other thing too is there's multiple what-if questions you can ask, as well as multiple relationships within here, especially as you explore the metrics. So I apologize for all the text, but it helps me along. But I just want to convey what it is that I'm doing here again, because I think it's challenging to move away from mathematics as practicing. This activity is not to inform students about gerrymandering, nor its history, or its politics, or even its implications, but just to encourage to engage mathematically with the issue. And by doing this, it provides a space to inquire and explore. The what-if strategy proposed by Brown and Walter provides opportunities for students to explore necessary implications on their own. Students don't know the issue very well. And that's not always true. Some of them do know the issue, but typically they won't. And that, I find, is a good thing. Typically they will create their opinions are based on what other people have told them. But by approaching it mathematically, they're not personally attached. They don't know the issue very well. They haven't made a decision already. And then they can be more playful and imaginative in their investigation. And they're invited to engage in this exploration through problem posing, not to achieve a particular outcome. The last thing I want to sort of discuss is that you know, I'm trying to deal with gerrymandering or try to figure out a fix. There is no fix. It's just really just understanding it in a different way. I used to use the term social justice, but I moved away from that, partly because it is just a reactionary response and people make their decisions before you engage in the topic. And so that's why I try to talk about social issues. So my wife is doing her master's in health statistics. And one of the courses she's currently taking is one on epidemiology, which focuses on the association between risk and health outcomes. And and so they work with, this epidemiology works with raw data and tries to come up with associations. And there's lots and lots of stories, but this is the one I've chosen because I found it really interesting. And just to go back to a story from 19th century England, in September 1854, there was approximately 600 people who died near a particular street pump in London. And the Receiver General at the time, and this was common belief, that the cause of cholera, and cholera, this is what was happening with cholera, people were dying, was that it was from low altitude, from a low-lying cloud. And so people at low altitude were more likely to contract cholera and pass away. And this data surprisingly supports that particular theory, which is kind of funny. We can laugh at it now, but you know, when you don't know how things are, where a virus or a bacteria is coming from, it's especially in the mid-19th century, they didn't know as much as we may know now, although we're still struggling with figuring out coronavirus too. But the point being is that mathematizing is also multiple, that it's not just about, mathematizing doesn't lead to truth. It doesn't necessarily clear up the situation. It doesn't necessarily convey to us what we need to understand. It's simply a way to explore numbers and relationships. And so Jon Snow, funny name, not from Game of Thrones, was a physician who actually thought, no, it wasn't from low altitude, it was from the water. And he collected his own data. He didn't get support from anyone. He collected door to door. He collected his own data and found that, in fact, that it was the water companies. One of the water companies, Lambeth, had their source further up the Thames River than the other two water supply companies, which had it closer to the city where the water was more polluted. And his data also supports that. The point being, though, is that mathematizing is not about truth or correctness. It's about understanding and exploring different relationships. So, mathematizing, it's directional, it's creative, and it's multiple, and it's rethinking the notion of application. And the social issues, is developing contextualized relationships and also engaging in critical mathematics. And the best example I can come up with critical mathematics is just scrutinizing mathematics like I did with the theater problem that I presented earlier. And just my own words, my conclusion is just that this mathematizing social issues is to show that mathematics is less about computation and algorithmic mastery and more about becoming a mathematizer. I like making up new words. The thesis of the project is to uncover possible mathematical foundations of social issues that rely less on reactionary responses and more on mathematical relationships. And the variation of those relationships using problem posing help develop an awareness of the social practices around us. So therein lies my presentation. I do apologize that I was talking so much, but I would love to open it up for discussion. As I said, this is not, I think I might have spoken definitively as if I found some new way. So far, the research and my own anecdotal research and informal research, yes, I think that this is profound, but I still have a long way to go, developing many more situations and mathematics around social issues. Each social issue will have its own mathematics. I think gerrymandering has a lot to offer. But again, you know, if we think of something like, let's say, racial profiling, how do you know how do you distinguish the difference between appropriately pulling someone over and questioning them and racial profiling? It's a mathematical question, as is climate change. We don't really experience climate change on a day-to-day basis. Some people might argue that, but ultimately it's change over a long period of time. And so the only way to really support understanding climate change is data. But again, how do you analyze that data? How do you mathematize it? Well, it's directional, it's creative, it's multiple, etc. Yeah, thanks for listening. I would love to have you turn on your videos and engage in questions or discussion. I'll stop sharing my screen so we can all see each other.